All right, in this video, we're going to work with variance in the F distribution a little bit. Here, let me start off with the definition. One-way analysis of variance, what we're just going to call from now on ANOVA, is used to compare the means of three or more populations. We will set up hypothesis testing. Like H sub 0 will be something like mu1 equals mu2 equals mu3, however many there are, say mu k, and then our HA will be that at least one of the means is different from the others. To perform this testing, we need the following. One, each sample comes from a normal or approximately normal population. The samples must be independent from each other. Each population must have the same variance. We're going to make use of the following test stat. This will equal the variance between samples divided by the variance within samples. And we're going to give these each names. We'll call the numerator ms sub b and the bottom ms sub w. We'll use the following degrees of freedom. The degrees of freedom in the numerator is going to equal k minus 1, and the degrees of freedom of the denominator will equal capital N minus k. What are these letters? K equals the number of samples, and N is the total number of items in all of the samples. we'll use the F distribution. Now, this test statistic is much more complicated than the ones that we've had before. So let's take a look at how we compute that. First, find the mean, let's call it x sub I bar, of each sample. Compute the mean of all items in all of the samples call it x bar, but then put 2 bars above it. This is the grand mean. So that's the mean of everything, all the samples, all the items in all the samples. Add them all up and divide by capital N. Compute the sum of squares between the samples. So what's that look like? We have SS sub B equals the sum. Remember, NI represents the number of items in sample I. And then what we do is we take the mean of sample I, subtract from it the grand mean, and square it. And then we're going to sum up all those things. Let's say n sub I equals the size of sample I. For compute the sum of squares within samples. Here we have SS sub W will be the sum of n sub I minus 1 times s sub I squared. Remember, s sub I squared will be the variance of sample I. For number 5, compute the variance between samples. Here we have MS sub B, that's going to equal SS sub B divided by DFN. 6. Compute the variance within samples. Here we'll have MS sub W will equal SSW, all divided by degrees of freedom in the denominator. And then finally, compute the test stat. That'll be F will equal MS sub B divided by MS sub W. All right, next let's take a look at the steps of performing one of these ANOVA tests. So we'll call this performing a one Way Anova Test. First part, this is the part that's usually going to be assumed in all the problems anyways. Verify that the samples are random and independent, and come from populations that have normal distributions, or at least approximately normal. As usual, next step, state H0 and HA. Specify alpha. The degrees of freedom in the numerator the degrees of freedom in the numerator is equal to k minus 1. The degrees of freedom in the denominator is equal to n minus k. K equals the number of samples, and n equals total number of all items in all samples. We'll do examples obviously for this kind of stuff. Next, determine the critical value F0. We have a test stat F equals ms sub b over ms sub w. We'll go in our example, we'll show how to do that as well. And then as usual, after all of this, make the decision. So I don't know if I've mentioned it before, but here's a couple of notes. ms sub b is also called mean square between. And you can imagine similarly, ms sub w is also called mean square within. Okay, we have an example here that's showing samples of different types of batteries. You have the group size 3565 and the 24/24F. I'm going to call these number 1, number 2, and number 3. So in particular, we have 3 samples. That means that k is equal to 3. Let me write that down. K is equal to 3 since we have a total of 3 samples. Also, capital N, the total number of items in all the samples is 15. There's 5 in each sample, times 3 is a total of 15. So we've got these things. That means that when I do get to the degrees of freedom in the numerator, remember that's k minus 1, that will equal 3 minus 1, which will equal 2. The degrees of freedom in the denominator is capital N minus k. That'll be 15 minus 3, which will be 12. So I'll be using those numbers at some point. But for right now, let me put down what we have. My H0 is that the 3 means will be equal to each other. And then my HA is that at least one mean is different from the others. Now let's go ahead and put this information in a calculator, because we do have to calculate things like the standard deviation and the mean, and that's best done with a calculator. So let me pop into there, and let me go into my stat, let me edit, and now in here I'm just going to delete everything I have there. Now since I have 3 samples, what I'm going to do is use 3 columns. So I'm going to use L1, L2, and L3. Let me move this out of the way and start putting in my data. So for this first row, group size 35, which I'm calling number 1, I'm going to put in L1. So let me go ahead and enter that. Alright, I've got my data. Now what I'm going to do is find the standard deviation and the mean for each one of these things. So let's go ahead and do that. So you can go to Stat, go to Calc, and just do one variable stats. Hit Enter, and you see it's going to do the list 1. So let me enter my way through this, and I'll get what I need from list 1. So you can see that X bar is 109. So I know that X1 bar equals 109. That's the mean of the first sample. Its standard deviation, S sub 1 squared equals, let's come back to the calculator and see what I have for it. They have 14.317, but I'm going to want it, this is the standard deviation that it gives me on the screen. I want its square. So what I'm going to do is I'm going to leave this for a second, quit. I'm going to go to vars, I'm going to go to number 5, I'm going to choose option 3 for SX, and then I'm going to square it. That's 205. Let me move on to the next list. So let me go back to my stat, calc, the one variable stats, but now I want to do it for the second list. So if you press second and then on top of stat there's list, choose list number 2 and then enter your way out of this screen. And so now we've got X bar is 174. And once again, it's going to give me the standard deviation and not the variance. So I want to square that S sub X. How do we do that? Get out of this screen. Vars, 5 for statistics, and then choose number 3, and then let me square it. Enter. 4792.5. And then finally X3 bar and S sub 3 squared. So I have to go into my stat. Once again, calc, one variable stats. This time we want to choose the list to list 3. So I'm going to go second, above stats is list, and I'm going to choose option 3. For list 3, and I'm going to enter my way out of this. So my mean is 114, and as I've mentioned now a couple of times, they give me the standard deviation. That's not what I want, so we can leave this screen, choose vars, number 5, choose 3, and now square it. 867.5. You'll also find that you get better accuracy this way because the calculator keeps more decimals in its memory or in its stack than what it is able to show on the screen. Now these just happen to work out very nicely, probably because it's an example out of the textbook. All right, let me remind us here. The degrees of freedom in the numerator is 2. The degrees of freedom in the denominator is equal to 12. Alpha equals 0.05. So let me get the critical F0 value. And once again, we need to go to the tables for that. All right, I've got the table for alpha equals 0.05. The degrees of freedom in the numerator is 2, and in the denominator is 12. So I'm going to go down the 2 column until I get to 12, which is right here. So I have 3.89 as my F0. And as you'll also recall, the F distribution is not in any way, shape, or form symmetric. So we just kind of draw these pictures. And let's see what my test stat does. For that, there's a lot of work to be done. For one thing, we need the sum of x1 numbers. So come back to the calculator. Let me see what I have on the screen. I do not. Let me come back to my stat. Let me go to calc. One variable stats. Let me go back to L1. I didn't know I would need this at the beginning, or I would have taken this information at the beginning. So once this is going to sum up, or this is going to give us the stats for L1, and I wanted sum of x, which is 545. And then I want to do the same for the second list, and I want to do the same for the third list. So stat, calc, one variable stats, change L1 into L2, and enter your way out of this. Sum of x is 870. And then x3, list 3, let me go to stat, calc, one variable stats, change that list to list 3, and enter your way through. The sum of x here is 570. All these are needed in the formula. Now, one of the things we needed to calculate was something called the grand mean. That was the one with x bar, but then it still had an equals on top of it. That's where you add up all of the numbers. So I take my 545 plus the 870 plus the 570, and I divide it by capital N, which is 15. So I'll have 1985 over 15, and this works out to be 132.3 with a bar over it. I'll probably use 4 decimal places in my computation, so I'll probably think of that as 132.3333. All right, now let's calculate some of these things that they want. The MS sub B. MS sub B. That equals SS sub B divided by the degrees of freedom in the numerator. SS sub B looked like this. This was the sum of Ni times Xi bar minus x bar 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 squared divided by k minus 1. Let me go ahead and put in these numbers. N1 is the size of sample 1. I'm going to do it this way. N1 times x1 bar minus x bar 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 squared plus N2 times x2 bar minus x bar 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 squared plus N3 times x3 bar minus x bar 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 squared. All of that is over k minus 1. Now finally let me put in my numbers. The sample size for every single one of these was always 5. And then x1 bar, let's see if I can find it again, is 109 minus 132.3 with a bar over it squared plus 5 times, now x2 bar, let's go and find that, that's 174 minus 132.3 with a bar over it squared plus 5 times x3 bar, where are you at? 114 minus 132.3 with a bar over it squared. All of that, we've done k minus 1. That is, k was 3, so this is over 2. And let's get the calculator to do this for us. For the most part, you can enter it the way it looks. So whatever screen you're in, it's a smart idea to quit it. And let me go ahead and put in my numbers. Now, you don't have to put a times or anything. You can just put in the numbers as you see them. And as I mentioned, I'm going to put 3, 3, 3, 3. Finish off the parenthesis and then square it. Plus, and do the same thing again. 5 times 174 minus 132.3333. Let me finish that off. Square it. Plus 5 times, I made a mistake, times, let me move this out of the way, 114 minus 132.3333. Let me square that. And now I'll enter for my final answer for the numerator. It doesn't like something I did, so let me go to the go to, and it looks like I used a negative instead of a minus. Gotta watch, I rely on the keyboard too much. Let me hit enter again, and it still didn't like, so let's take a look at my go to, and it still has the same thing there, a minus where a negative should have been. And then I think I probably have one more. Once again, a negative where a minus should have been. Now let's see if we're done. Good. So I get 13083.3333. I still have to divide that by 2. Luckily, all you have to do on the calculator is do this. Divide, press 2, enter. I get 6541. And I'll go to 4 decimal places like so. So I've got the numerator of my test statistic. Now let's go for the denominator. MSW equals SSW over DF sub D. And what that is, the definition is the summation of Ni minus 1 times S sub I squared, all of that divided by DFD. And so when I write them out, I'm going to get N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared plus N3 minus 1 times S3 squared. All of that is divided by capital N minus K. Now let me put in my numbers. All those N numbers are equal to 5. So I get 5 minus 1. S sub 1 squared. Let's see if I can find it again. It's all the way up there, which was 205. Plus 5 minus 1 times S2 squared, which is 4792.5. Plus 5 minus 1 times 867.5. All of that is over n was 15, k was equal to 3. And so let me write one more thing before I get to the calculator. Just a small teeny bit of simplifying. All right, let me go ahead and tack the numerator like I normally do. You can do it all in one shot if you're willing to use parentheses around the numerator, but I'll do it in 2 steps. So 4 times 205 plus 4 times 4792.5 plus 4 times 867.5, and now let me hit enter. So I get 23,460 divided by 12. So once again, all I have to do is click the division button, put in 12 and enter, and I get 1955 exactly. So that's my MSW. And up here, this is my MS sub B. So now I'm ready for my test statistic. F equals MS sub B divided by MS sub W. So for the MS sub B, we have 6541.6667. MSW is 1955. And let's let our calculator do its business. 6541.6667 divided by 1955. Enter. 3.346. So there's my F. Now I had the picture up there somewhere. Where did it go? Wow, it's way up there. All right, let me go ahead and grab it. All right, I brought my picture back, and if I look, my 3.346 is close, but not quite in the rejection region, so we do not reject H naught. Now, as always, with these things, I always show the p-value method as well, so let me go ahead and do that. And I think this is where you really appreciate the calculator quite a bit. I can calculate p-values and all that stuff by making use of one of the apps inside of the calculator. Let me move it to the side. And what we do is we go to Stat, choose Tests, and go to the last test in the whole list. You see that it's ANOVA. Hit enter. Now all you have to do is put the lists that you have data in. So remember where they're at. Second above stat is list. I'll choose L1. So I'll choose number 1. Put a comma. And then next choose number 2. So second stat, choose number 2 for L2. Put another comma. And once again, go to second stat, to choose L3. Finish the parenthesis and hit enter. Give it a moment, but what you see here, look, it gives us the test statistic in here. What I used was ANOVA L1, L2, L3. What it gives back is the test stat, which we don't need for the p-value. Well, actually, that's how you determine the p-value, is f equals 3.346. And you saw we did all that work earlier in getting that. What I want, though, is the p-value. P is equal to what? They have it right there, 0.07. Alpha was equal to 0.05. So we see that p is greater than alpha, which means that we reject H naught. You can see then how you can use this to do these problems very quickly. All you have to do really, if you're going to make use of the Anova app, is simply enter the data inside of the calculator, and it will give you everything that you need. Let me show you a few things more that it gives you. So let me come to the calculator and let me grab that screen. All right, what they have here, let me show you what the calculator is giving you. This degrees of freedom there, that is DFN. This SS is SS sub B. This MS is MS sub B. Now there was a second screen associated with this as well. If you hit the down arrow, it'll give you the next page, I believe. There we are, in the error. Keep going down until we uncover. Let me go as far as I can, and there we go. Now for the other page, that DF that they're referring to there, that is DFD. That SS there is SSW. And that MS there is MSW. So you have any kind of information you could be asked is found here. All you have to do is enter the data into the calculator. Let's do some more examples. All right, here's an example, another example that we had that shows government salaries from the federal, state, and local. And they're trying to determine if the means of these three items are the same. So as usual, we'll set up hypothesis testing like this. mu1 equals mu2 equals mu3, and then HA would be at least one mean is different from the others. All right, so the first thing you want to do is enter this data into the calculator. Let me do that, and then we'll continue. So if you remember, go to Stat, Edit. Now, since we have more data here than I had before, I'm going to just overwrite the old data. And before I do, let me say that this will be 1, state will be 2, and local will be 3. You could do mu sub f, mu sub s, mu sub l if you want, but I think it will be confusing when you get too many subscripts going on like that, but you do what you need to do. Now we enter the data. All right, so now that I've got all the data entered, I can go to Stat, go to Tests, go to the very bottom, Anova, and then put in L1, comma, L2, comma, L3. Finish the parenthesis and hit enter. So I've got my F test statistic f was equal to, and then I've also got the p-value. And these are never exact, but let's go ahead and see what my f was. My f was 34.331. And my p-value is 3.832 times 10 to the negative 8. And if you'll recall, that's the same as having 7 zeros before the first 3. Like that. So with our alpha equals 0.01, we could see that p is a bit less than alpha, so we would reject h naught. So doing this using the p-value method is extremely quick, as you can see. I can still do the classical method. That's not hard either. I mean, after all, the calculator did give me my f value. It gave me 34.331. Now, what we need are alpha equals 0.01. I need the degrees of freedom in the numerator and the degrees of freedom in the denominator. You can get those from the calculator, or you can just do them yourself. We have a total of 3 classes, if you will, or 3 samples. So I have 1, 2, 3. Degrees of freedom in the numerator then is 3 minus 1, which is equal to 2. The degrees of freedom in the denominator, that was capital N, so that's 15. I made a mistake. Here we have a total of 10 times 3, so we have a total of 30, minus k, which was 3, so we have 27. Now let's go to the table where alpha equals 0.01. Here we have my alpha equals 0.01. Now I need a degrees of freedom in the numerator 2, and in the denominator 27. So let me pop down to 27, and I see that my critical value is 5.49. So F naught is approximately 5.49. And then when you draw a picture, .49, our F value is way buried into it deeply. So we know from this to reject H naught. Here I'm going to do one last example. This involves hospital stays and how long people are in there. This kind of information is extraordinarily important to insurance companies because they're very strict about the number of days you spend in the hospital for certain procedures. Let me first go ahead and get my data into the calculator. And notice we don't have the same sample size for all of them. That's not important. Go back to Stat, go to Edit, and I don't have as much data as you had in the previous, so I'm just going to use the delete button to wipe everything out. Now, since you have 4 samples, you're going to have to use L1 through L4. And let me go ahead and put in the data. All right, now that I've got my data in, since I'm right here, let me go ahead and calculate the things that I need. So go to Stat and then Tests, go to the very last one and choose Anova, and then put in L1 through L4 separated by commas. Once you get them all in, finish the parenthesis and hit enter. Let me hold off on that data for a minute. And let me put down the null and alternative hypotheses. My null hypothesis is going to be that mu1 equals mu2 equals mu3 equals mu4. So once again, 1, 2, 3, 4. Keep track of what you're using. You can use letters as well. All right, so my H sub A is that at least one mean is different from the others. All right, my test stat came from the calculator. Let's see what it is. I have F equals 0.557. And my p-value is what? 0.648 to 3 decimal places. All right, let's take alpha was what? Alpha is over here, 0.01. Alpha equals 0.01. So since p is greater than alpha, we do not reject H naught. All right, to finish off this video, let's go ahead and do the classical method. Here we already have our alpha equals 0.01. The degrees of freedom in the numerator equals k minus 1. We have 4 samples, so k is 4. 4 minus 1 equals 3. The degrees of freedom in the denominator equals capital N minus k. That equals capital N, the total number of items in all of these samples is, let me see how many we've got in this first sample. We've got 3, 6, I've got 9 of them. 18 plus 7 more is 25. Plus 8 more is 33. So we have 33 minus 3, minus 4. That's 29. And so I need to go to the 0.01 table. Let's go ahead and take a look at it. And then I need 3 and 29. So the 3 column for the degrees of freedom in the numerator. And let me come all the way down to 29. Let me scroll underneath of there. There's 29. It looks like it's 4.54. So F naught is approximately 4.54. And when we draw the picture, 4.54. Let's take a look at our test statistic. And let's go ahead and slide it all the way. It's all the way still in the white area. So we do not reject H naught.